And on to problem 2. Problem 2 says researchers on a boat are investigating plankton cells in a sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter is modeled by P of h equals 0.2 h squared e to the negative 0.0025 h squared for 0 less than h less than 30 inclusive, and is modeled by f of h equals h is greater than 30. This continuous function is not explicitly given. They want us to find p prime of 25. So they're asking us to find the derivative of this function. So I'm going to do differentiate, and I'm going to type in my function, which is 0.2 h squared times e to the negative 0.0025 h squared. And I want to integrate this with respect to h, and I want to do this at h equals 25. And so when I do this, I find out that p prime of 25 is equal to the integral, or not, excuse me, the derivative of that. So it's the derivative of p of h at h equals 25, which is negative 1.17906. And keep in mind that this is a rate of change, so this is going to be million plankton per cubic meter per meter. In other words, the density of plankton is decreasing at negative 1.179 million plankton per cubic meter each meter at h equals 25 meters. So that's my justification, that's my explanation, and that's part A. So now moving on to part B. On part B it says, consider a vertical column of water in the sea with horizontal cross-section of constant area 3 square meters. To the nearest million, how many plankton cells are in this column of water? So I have some column of water. I have no idea what the shape is, but I know that if I take any cross-section of this, I know that the area is 3. And I know that if I ever want to find volume, all I have to do is integrate area with respect to some length. And I know that in this case, I want my depth to go from 0 to 30 meters. So if this is volume, and I know the density, then the number of plankton is going to equal the volume times the density. The only thing is that my density is actually a function of h. So I need to make sure that I'm going to integrate from 0 to 30 my area function, which is 3, times my density function, which is 0.2 times h squared times e to the negative 0.0025 h squared dh. So I'm going to do that integration. So we're going to do calculus 2, excuse me. Stop it. Calculus 2. We're going to integrate 3 times 0.2 times h squared times e to the negative 0.0025 h squared. And I want to integrate this with respect to h from 0 to 30. And we end up with 1,675.41 million plankton. Of course, they're asking us to do this to the nearest million, so we'll go ahead and take care of that. That's how many plankton it is to the nearest million, 1,675. On to part C. Part C says there is a function u such that 0 is less than f of h is less than u of h for all h greater than 30, and the integral from 30 to infinity u of h dh is equal to 105. The column of water in part B is k meters deep where k is greater than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column, and explain why the number of plankton cells is less than or equal to 200 million. Well, if I'm trying to find the number of plankton, then what's going to happen is I'm going to be doing the integral from 0 to k of this f of h. But I know that this happens to be less than or equal to the integral from 0 to infinity of f of h dh, because my plankton have to be, if I go deeper, I have to have more plankton. That's just a rule of the ocean. And I know that this is equal to the integral from 0 to 30 of f of h dh plus the integral from 30 to infinity of f of h dh. Because if I have a big interval, I can always split it up into two smaller intervals. And I happen to know that this is less than or equal to the integral of this, which is exactly the same, plus the integral from 30 to infinity of u of h dh. But I know that this is 105. And I know from the previous problem that this was how much? 1,675. And I know that this is less than 2,000 millions. So that's how I can justify this. This is why I can explain that that's going to be less than 200 million. So I've written an expression here using one or more integrals that gives us the plankton cells in millions. Now, if I wanted to, I could make this slightly different and write this as the integral from 0 to 30 of f of h dh plus 105. And I could say that that's going to be strictly less than, because I know this is true. Not strictly less than, just less than or equal to. So that's part C. Let's take a look at part D. On part D, it says the boat is moving on the surface of the sea at time t equals 0. The position of the boat is given by this parametric expression x of t, y, and t, where x prime is given by 662 sine of 5t and y prime is given by 880 cosine 6t. Time is measured in hours, x and t and y of t are measured in meters. They're asking for the total distance, and I know that the total distance between points A and B can be written as the square root of x prime squared plus y prime squared dt. So I'm going to be integrating from 0 to 1, the square root of, this is going to be 662 times the sine of 5t that I'm going to be squaring. And this is going to be 880 times the cosine of 6t that I'm going to be squaring. And I'm going to be integrating this with respect to t. So I'm going to be integrating the square root of, so I'm going to take this whole thing and raise it to the 0.5 power. And inside here, I'm going to take something and square it. And the thing I'm going to square is going to be 662 times the sine of 5t. And I'm going to add something squared. And the something squared that I'm going to add is the 880 times the cosine of 6t. And I need to make sure I'm closing parentheses as I go. So this needs a closed parentheses there to make sure that that whole expression is being squared. And this 880 cosine of 6t also needs a closing, then close to square, and then that whole thing's being square rooted. And I want to integrate that with respect to t from 0 to 1. And while we're waiting, And so we end up with 757.456. And because they tell us x and t and y of t are measured in meters, that's the units that we're using. Okay, so there is problem number 2. And so that's our calculator section. So let's go ahead and get rid of our calculator.